Okay, in this example, a tractor trailer has a spring fitted with the deflected 10 centimeter under the weight of the trailer of mass 500 kilogram. Dashboard are fitted between the road wheels and the body such that the damping ratio is equal to 0.4 of the critical damping. The trailer is pulled along a road with an approximate sine wave contours. The distance between the successive peak is 15 meters and the depth between the peaks and valleys are 5 centimeters. Assume that the wheels do not leave the ground and that the tires are stiff compared with the spring. Find the variations in the force in the springs and the amplitude of the vertical movements of the body of the trailer. If it is pulled at 60 km per hour. Okay, this is the example problem we are going to discuss. Okay, let me draw the sketch including the details first. Okay, let's take this is the tractor trailer tires. It is pulled with the velocity. What is the velocity? 60 km per hour. 60 km per hour. So then what is the road? It has the sine wave contours for the road like this. Okay, sine wave contours for the road. Then this in between the two peaks, the 15-meter distance, and the peak to valley height is equal to 5 centimeter. Peak to valley height is equal to 5 centimeter. This height is equal to 5 centimeter. Okay, this is the problem. So then the equivalent system we can draw for this problem is the equivalent system. Here it is 500 kilogram. The 500 kilogram the body of the trailer. Then this is the spring stiffness and also the dashboard successive. Then the vibration coming from the base. Okay, vibration coming from the base. Base is exciting, forming this kind of sine wave. It having this kind of function. Okay, sine wave function. Okay, so okay, so then what are the we can calculate the stiffness K first. How to calculate the stiffness K? That data is given. So because of the vehicle weight of the trailer, the spring deflect 10 centimeters. So that using this simple equation, the F is equal kx, we can calculate the k. K is equal to F divided by x. What is the F? 500 into 9.81. Okay, 500 into 9.81, the weight of the trailer, divided by the x, the deflected amount in meters, the 0.1. So then k we can calculate, the k is equal to 49.05 kilonewton per meter. Okay. Then also we can calculate the omega f. That means this frequency we can calculate. First of all, we have to convert vehicle velocity. What is the vehicle velocity? 60 kilometer per hour. Then I am going to convert into a meters per second. 60,000 divided by 3,600. So then the meters per second. So that is equal to 16.667 meters per second. Okay. So then this road having the irregularities, this wavelength is equal to 15 meters. Okay, so then omega f we can calculate. That means cycles per second. So first of all I am going to calculate the cycles per second. Cycles per second. In 1 second, this is the distance it move. So how many cycles per second? The cycle length is equal to 15. That means lambda is equal to 15. So then we can calculate easily cycles per second. 16.6667 divided by the 15. That will give cycles per second as 1.111 hertz. Okay, these are cycles per second. Then we can cycles per second. Then we can calculate omega, base excitation frequency. So I will put the omega f, base excitation frequency. This is the cycles per second. So then I by converting into a radians per second, by multiplying the 2.5, then we are getting the radians per second. That value is equal to 6.9813 radians per second. This is the base excitation frequency. In this much of frequency, the base is exciting. The amplitude of the base excitation is equal to this peak height is equal to 2.5 centimeter. That is given as a data. Okay. At the same time, we can calculate system natural frequency. What is the system natural frequency? Omega n is equal to k divided by m square root. What is k? 49.05 into 10 to the power of 3 divided by the 500 into square root. Okay. Then I have already calculated this value. That value is equal to omega n value is equal to 9.9045 radians per second. Okay, radians per second. Then these data given in this problem. So then again I am going to calculate the frequency ratio, that omega f divided by the omega n. This ratio is we need in later calculations. So I am going to calculate that one. 6.9813 divided by 9.9045, that is equal to 0.70486. And also this ratio also very important. That means square of this ratio, omega f divided by omega n into square, that is equal to 0.4968. Okay, from this given data we can find these things. Okay, in this problem, these given data we can find the frequency ratio, and also the system natural frequency, and also the forcing base excitation frequency we can easily calculate, and also the spring stiffness also we can calculate. Okay, these data we can easily calculate from the given data. Okay, then problem is asking to find the amplitude of the vibration. That means x we have to calculate. Okay, when solving this kind of a problem, when discussing the theory classes, I explain the for this kind of system base excitation system, M, K and C. For the base excitation system, steady state vibration is given by xt is equal to x cos omega t minus 5. Okay, omega f t minus 5. Here this is the steady state vibration. Steady state vibration is given by this equation. When discussing the theory classes, we obtain the expression for the x. What is the expression for the x? So we obtain x is equal, that means the amplitude of the vibration of the m mass, the x, we have obtained this equation 1 plus 2 theta omega divided by omega n into square divided by 1 minus omega divided by omega n into square of total plus 2 theta omega divided by omega n into square root of total. This is the equation we obtain for the x. Okay, then this problem also asking to find the x. So I am going to substitute these found values. This equation already we know theta, the frequency ratio already we know. So then all the data we know, we just want to substitute this data to find the x. So then x value is equal, so 1 plus 2, the damping ratio is equal to that is given in the as the data, and also the frequency ratio, what is divided by omega n, that is equal to, we already calculated that value, 0.700486, the square of this total divided by 1 minus square of this term, is already calculated 4.968, then the square of total plus 2 into 0.4, then omega divided by omega n, 0.4968 into square of total, square root of total. Okay, square root of total. So then this is the finally if we substitute these values in this equation, finally we are getting this one. So then I have already calculated this x value. For the x we are getting 3.797 centimeters. So then there's approximately, that is equal to 3.78 centimeters. Okay, this is the amplitude of the vibration. That means this body is vibrating with this much of amplitude. That means the body is vibrating, forming this kind of curvature. This amplitude is equal to 3.78 centimeter, and also because of the base excitation. What is the base excitation? The base excitation, something like this. Base excitation is a sine function. Uh, 2.5 centimeters. Because of this base excitation, this is vibrate forming this kind of amplitude. Okay, this kind of amplitude. Then again the problem also asking to find the force generated by the spring. So then how to calculate that one? Force generated by the spring. The second part of the problem asking to find the force generated by the spring. Then how to calculate that one? Then let's take, this is the body of the vehicle, 500 kilogram. Then this is the spring. Then this is the dashboard. Okay. Then Let's take the certain position t is equal t. T is equal t. Then this is base is exciting with the yt function. This is also, because of this base excitation, the mass also moving with the xt movement. It produces the xt movement. You can see at the t is equal t position, the base has moved by the y distance. This m mass moved by the x distance. So what is the total compression of the spring? Total compression of this spring. What is the total compression of the spring? Here, because of the x movement, it is extract. Because of the y movement, it is compressed. So the total compression, relative compression, y minus x. Y minus x. So we can write this one as the yt minus xt for certain time value. For certain time value. Okay. For a certain time value. So then how to calculate the spring force? The force generated by the spring. So the force generated by the spring. How to calculate the force generated by the spring? So the total compressive force we are calculating, that is equal to K, spring stiffness, yt minus xt. That will give the force generated by the spring in this moment. So then how to calculate that one? Then I will take this force as F, that is equal to K. We have already calculated this K value. What is the K value we obtain? Okay. The spring stiffness already calculated. That is equal to 49.05. Then we are getting the, if we substitute the y in meters, we are getting kilonewtons. Okay. Then yt for time t, what is the displacement of yt? So then base is exciting, forming the sine curve. Base is exciting, forming the sine curve. So then in a t, the time is equal t position. What is the displacement? Yt is equal the 2.5 into sine omega t. 2.5 into sine omega t. 2.5 sine. So then this one we have to convert into a meters. So yeah, F is equal 49.05, 2.5 into 10 to the power of minus 2 sine omega t minus what is xt? Xt is given by the equation. Xt is equal x cos omega t minus 5. Okay. Then how to calculate the xt? The x already we calculated. What is the x magnitude? 3.79 into 10 to the power of minus 2. Then the cos, what is the forcing function frequency? We already calculated the forcing function frequency, omega f, 6.98 into t minus 5. What is 5? 5 we have to calculate. To calculate the 5, we have an equation. To calculate the 5, we have an equation. 5 is given by this equation. Tan inverse 2 theta omega divided by omega n into 3 divided by 1 plus 4 theta square minus 1 omega divided by omega n. This is the phase shift with the base excitation. So then I am going to substitute the values. The 5 is equal tan inverse, what are the values? 2 theta, 2 into 0.4 omega divided by omega n 0.7 0486 into cube divided by 1 plus 4 into theta square 0.4 into square minus 1 omega divided by omega n 0.4 0.4968 yeah, it is equal to. So then I have already calculated this value. The 5 is equal, if we simplify this equation by taking the tan inverse, we are getting the answer 18.84 degree. So if we convert into a radians, 0.3288 radians. Okay, 88 radians. So then I am going to substitute this value in this equation, the sine omega t. So then the xt is equal x cos omega t minus 5. What is x? X already we calculated 3.79 into 10 to the power of minus 2 cos omega t minus 5. What is omega? Sorry, 6.96 into t minus 5 0.3288. This is the answer for that one. I will write that answer. Let me write that answer. Okay, let me write the final answer for this one. If is equal 49.05, then 2.5 into 10 to the power of minus 2 sine omega. Sine omega mean forcing function frequency 6.9813 sine omega t minus 3.79 into 10 to the power of minus 2 cos sine omega t minus 5 omega t minus 5. What is the 5? Phase shift 3.288. Okay, this is the final answer we are getting. So then we can further simplify this equation. If t is a function of time, it's not a constant value, it's a function of time. It is dependent on the function of time. 0.4905 2.5 sine 6.98 I will round it to two numbers, 30 minus 3.79 into cos 6.96 into t minus 0.329 in kilonewtons. This is the force generated by the spring in deformation. in deformation mean in vibration the base due to the base vibration the this mass also vibrating, forming this kind of curvatures. So we have to take the resultant compression. That means delta x of is equal to y minus x. So by multiplying with the k we can calculate the f, how it is vary with the time, yt minus xt. So then we are, by substituting this yt and xt in this equation, we are getting this equation. It is a function of time. It's it is vary with the time. Okay, this is how we are solving this example problem. Okay, thank you.